Mixture weight is a very good example of Bayesian inference and modeling. We'll take a close look at it in this talk. Next slide. Mixture weight is an uncertain quantity in the STR experiment that can be very well modeled as a random variable. We can infer the mixture weight from the STR experiment data. We use the quantitative peak data and also assume the contributor genotypes. A more sophisticated modeling that I won't address in this talk would also account for PCR stutter, relative amplification, peak variance, and degraded DNA and other factors. The formula for this as a posterior probability is that the probability of the mixture weight variable, capital W, assuming a particular value, say between 0 and 1 if it's a two-person mixture, or a set of numbers that add up to 1 if it's more than two contributors, is conditioned on the data, the first genotype allele pair value, and the second genotype allele pair value. These are represented in a hierarchical Bayesian model, which I'll draw a picture for in just a moment. I should note that more details about the methods in this talk can be found in our forthcoming Journal of Forensic Sciences paper on validating true allele DNA mixture interpretation. Next slide. Here is a graphical representation of the mixture weight probability model. We're focused on the kth contributor. There can be any number of contributors. And we'll first take a look just at what's shown in blue. At the bottom, we have the template mixture weight. This expresses the relative quantity as a number between 0 and 1 of what fraction of this contributor's DNA is actually present in the PCR template prior to amplification. Now, when you do the amplification, at each locus a separate experiment occurs, and so each locus has its own weight. These are related to the template weight in that there's some random stochastic variant of what that underlying weight is, and those are shown in the row above called locus weights. In order to calculate the template weight using Bayesian calculation, we need a prior and a likelihood. In this case, the template weight, shown as the bottom blue point in this graph, W sub k, has as its prior, shown in brown, say a uniform probability over all different possible mixture weights, and its likelihood is comprised of the locus weights. Now, when you go to calculate a locus weight by Bayes' theorem, it needs its own prior and its own likelihood. So for each locus weight, say W sub k1 for the first locus and the kth contributor, its prior is the template weight. And above it, its likelihood function is formed by the one or more experiments that involve this particular locus for that template. To do a Bayesian calculation, one would compute the template weight given its prior probability, shown in brown, and the locus weights as its likelihood, and then next compute each of the, say, capital N different locus weights as their separate variables with its own prior, the template weight, and looking at the experimental data. By iterating back and forth between the template and the n loci, back to the one template, up to the n loci, doing this over and over again hundreds of thousands of times, you can arrive at the probability distribution for the template mixture weight as well as the locus mixture weight for each experiment. Next slide. Let's take a look at how we can estimate the mixture weight for one locus experiment. This is something that DNA analysts who work with quantitative data and estimate mixture weights would find very familiar. So we're looking at one locus, and we're considering all the different peaks that are considered to be a part of the data. We focus on the peaks that we can ascribe to the kth contributor, say the first contributor, and we add up those peak heights. That's the numerator. In the denominator, we take all the allelic peaks and all their heights. We add up all those peak heights from all the contributors, That forms the denominator. The ratio of the sum of the peak heights from the kth contributor divided by the sum of the peak heights from all contributors forms an estimate of mixture weight at that locus. Next slide. Let's apply this experiment estimate to some real STR data, in this case from the Foley homicide case. At locus D16, we see 3 alleles. The very tall peak at 12 corresponds to the homozygote genotype of the victim, which is a 12-12, and the much lower 11-13 represents a much smaller quantity of a second contributor. Next slide. We can take a look at these 3 alleles at 11, 12, and 13 and examine their quantitated peak heights. We see that allele 11 has a peak height of 500, 12 has a much taller peak height from the victim of 6,750, and allele 13 from the unknown contributor has a quantity of 250 RFU. Next slide. Now we can form our experiment estimate of the mixture weight. We take the 2 blue contributor alleles, 11 and 13, and we add up their quantities, 500 plus 250. Then we divide by the total of the peak heights of all 3 quantities. 500, 6,750 plus 250 for all 3 alleles gives a sum of 7,500. Taking the ratio of just the blue contributors' alleles divided by the sum of the peak heights of all the alleles gives a mixture weight estimate of 10%. Next slide. Let's do this calculation again at a different locus. Here at D7, we had 4 alleles in the evidence data instead of 3. We see the 2 very tall alleles from the victim, 8 and 12, and we see the 2 much, much smaller alleles, 10 and 13, from a second contributor. Next slide. For these 4 evidence alleles, we see the 2 very tall alleles from the victim, 8 and 12, having RFU peak heights of 4,000 and 3,000 respectively, while the 2 smaller blue contributors' alleles of 10 and 13 both have peak heights of 250. Next slide. We can now form our experimental estimate of the mixture weight at this D7 locus. To estimate the fraction of DNA in the template at this locus that came from the unknown blue contributor, we add up the 2 minor contributor peaks from blue, alleles 10 and 13, as 250 plus 250 in the numerator, and then we divide by the sum of all 4 peaks of what their heights are, 4,000 plus 250 plus 3,000 plus 250. So in the numerator, we have 500 RFUs representing the amount of DNA from the blue contributor divided by 7,500 representing the amount of DNA from all of the contributors. The ratio in this case is 6.7%, so that forms an estimate at the D7 locus of what is the fraction of the blue contributor relative to the total. Next slide. In the examples I've shown so far, and in most laboratories' methods when they manually compute, either on paper or with a spreadsheet, the mixing proportions at each locus, they tend to only use those loci where the different contributor alleles can be clearly separated. That is, all of the first contributor's alleles form one set, and all of the second contributor's alleles form a disjoint set with no overlap, and so on if there are more than 2 contributors. However, that isn't necessary with computers and using matrices and vectors, as we described first in our linear mixture analysis paper in the Journal of Forensic Sciences 10 years ago. You can algebraically separate those out to estimate the mixture weight at any locus regardless of the constellation of the different alleles. Next slide. After you've formed estimates at every locus for the contributor, indicated here by little w sub k for the kth contributor and n for the nth locus, you can take the average over what you've seen at all the loci to get an estimate of the template mixture weight. That's mu sub k is the average of the mixture weight of the kth contributor, and it's just 1 over n times the sum. It's the arithmetic mean. With the identical data, you could also calculate the variance. How broad is the variation between the different mixture weights at the different loci? And to do that, here's the standard variance formula, which simply takes the square difference of each mixture weight at each locus from the mean weight that you calculate, squares it, takes the average. That's the variance. The square root would be the standard deviation. This is easily done in Excel. Next slide. Once you've computed the mean and the standard deviation of a set of numbers, in this case mixture weight estimates at each locus, you have described a probability distribution. In this case, the probability distribution of the template mixture weight. The mean is the central location here at 6.7%, and the standard deviation describes the breadth or dispersion away from that central tendency, which in this case is under 1%. Shown at left, taken from the true allele viewer interface, is what the mixture weight probability distribution expressed as a histogram looks like for the Foley case. We see a nicely centered normal distribution with a mean of 6.7% and a very tight standard deviation of 0.9%. Next slide. Standard probability theory tells us that the more data experiments that we have for a template, the greater precision we can get for the mixture weight estimate. For example, to double the precision, you can quadruple the number of experiments. In practice, having 2 multiplex amplifications can give you far more mixture weight precision than just having a single amplification. This is another example of how to use standard likelihood ratio methods to combine evidence from multiple experiments in order to obtain a more informative results. By multiplying the likelihoods together and then multiplying by your prior probability, you can arrive at the posterior distribution of the mixture weight variable of interest. Next slide. We can obtain a probability solution to a probability model that has multiple interacting variables. Let's see how. The first line says that the mixture weight W, conditioned on D, the data, G1, the first genotype value, some allele pair, and G2, a second genotype value, another allele pair, and comma dot 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 means the other hundreds or thousands of variables that are being considered, like stutter, prefamp, and so on, will form a posterior probability distribution. We can create a probability distribution, as we just saw, for the continuous variable W, mixture weight, conditioned on all the other variables. And then the way the standard method works is you randomly draw a mixture weight value from that probability distribution. Fine, that becomes your new W. Move to the second line. To now come up with a value for the first genotype, what that first allele pair would be, we see that the probability of the first genotype conditioned on the data, D, the second genotype, G2, the mixture weight value, W, and so on for all the other variables, also forms a probability distribution, which we talked about before. So you use Bayes' theorem and likelihood functions in order to try out every possible value, and you end up with a likelihood times a prior and a posterior distribution, and hence a probability distribution over all the allele pairs at some locus for, in this case, the first contributor genotype, and then you randomly sample from that probability distribution and select a new genotype value. You do the same thing on the third line, but now for the second contributor at a locus for its allele pair value. conditioned on the data, the first genotype value, the mixture weight, all the other variables. From that posterior probability distribution over all the possible allele pairs at that locus for the second contributor, you randomly sample and obtain a new allele pair value for the second contributor at that locus. Continuing down to the fourth line, which is really the next 100 or 1,000 lines, you repeat this process of creating a probability distribution, the posterior depending on the likelihood and the prior for every random variable in the problem, and then randomly sample and update the value of that random variable. After you've finished going through all the 100 or 1,000 variables, that constitutes one completed cycle. You then repeat this process tens or hundreds of thousands of times, and the laws of probability say that you will arrive at a posterior distribution for the probabilities of all the variables in your system. And this is how you find probability distributions by iterative sampling. It takes a lot of computing power and a lot of computing time, certainly a lot of mathematical modeling, but it provides an automated, rational, scientific, highly mathematical solution to describing the experimental process with mathematical modeling and arriving at probability solutions. The first paper that put all of this together and showed how to solve problems in this way was Gelfand and Smith 20 years ago, which very much revolutionized scientists' ability and social scientists' ability to solve virtually any real-world problem in which there was data uncertainty. Next slide. This class of methods is known as Markov chain Monte Carlo. A Markov chain is a probability method. It's a stochastic process that has no memory of its history. At every point in the process, it uses the rules of probability that have been laid down for it to randomly determine what its next step will be. Monte Carlo refers to collecting sampled points of some process, some random process, and using it to form a probability distribution. When you put the two together, you have a Markov chain that makes no decisions based on the past, and Monte Carlo, which records the past. Let me show you how this works. In the first row, we see a trace of the different values of mixture weight for the template in the Foley case. We've already arrived at the posterior distribution, so we see some minute oscillations around a number around 7%. Every cycle, there are about 10,000 cycles here, the computer goes through all of its 100 or 1,000 variables, the genotypes, the stutters, all the mixture weights, the uncertainties, the peak uncertainties. Most every variable in a modern probability model has its own associated uncertainty variable, not just the peak heights. So it goes through the 1,000 variables, and then one of those variables is the template mixture weight. So it repeats that entire cycle, say 10,000 times, never looking back as it makes the decision, that's the Markov chain part, but always recording where it has been, that's the Monte Carlo part. And this little trace that looks like a fuzzy line with a felt tip pen that's moving along the axis is very stable, and when it's all done, you look at what you have. Looking at the second graph here, we collect all those points into a histogram. The computer can do it differently, but for people visually it amounts to the same thing. The central tendency of the bell curve, the normal distribution that we arrive at, is at 6.7%, and the standard deviation, as we saw, is about 1%. This is the posterior probability distribution of the template mixture weight as computed in the Foley case using True Alleles Markov chain Monte Carlo probability search. Next slide. The True Allele system is a fully grounded Bayesian probability model, and therefore it must have priors and likelihoods. These formulas are taken from our JFS paper. And we see our description of belief before we ever see the data. For the genotype, our belief, looking at f squared or 2f1, f2, is that it follows the allele frequencies and in the population and Hardy-Weinberg equilibrium. If we have not seen any data yet, the genotype prior is the population prior. For mixture weight, we choose a prior that's completely uniform because we really don't know in advance how much of each contributor would be. The DNA quantity, M here for mass, is relatively broad over all possible RFUs, and the variance parameters describe positive numbers that could be used as a variance number. Next slide. True alleles likelihood function is joint over all the data and parameters. In the first line, we see that the data, D, at any locus, are described as a multivariate normal distribution, just a bunch of bell curves, at a mean pattern value and a variance that describes the peak uncertainty. The mean value mu is described in the next line. That's the pattern that's equal to the mass of how tall the peaks are times the weighted sum of genotypes, the sum of W, the weights, times G, the genotypes, that we've been seeing all the way through in the pictures. So that sum represents the pattern, and M, the mass, represents how tall the pattern is. The next line shows that this can be customized to each locus. And then the last line shows that the variation is equal to a scale factor, the peak uncertainty sigma squared, times the peak heights in accordance with chemistry and statistics and general physical principles that variance scales with the quantity, plus a background term. Next slide. The result of all this probability modeling and statistical computation is that the true allele system can compute the posterior probability for all of the many hundreds of different parameters that it models. For example, the posterior probability of a genotype, that Q has some allele pair value X, conditioned on the data, is proportional to the prior times the likelihood. In the next line, we see that the posterior distribution for each mixture weight variable is that it's proportional to the prior of mixture weight times the likelihood. If you take a look carefully at those likelihood terms on the right, you'll see that they're all probability of the data given the various parameters. What makes it different for each variable is which one is being changed, what's being varied. So the expressions are the same, but what's being changed, whether it's genotype in the first line, mixture weight on the second line, or data variation on the third line, is the only thing that's changing in the likelihood function. And of course, amongst the hundreds of variables, data variation and how much play there is in the peaks and what they're trying to tell us about the certainty of the data, which is critical for accurate DNA interpretation, is shown on the bottom for the scale parameters sigma squared and tau squared. That's the data variation conditioned on the data that were given in the problem along with the rest of the probability model. They're each proportional to their prior distribution times their joint likelihood function over all the relevant data for that variable. Next slide. This use of probability modeling of all the important variables in the STR experiment, along with Markov chain Monte Carlo statistical search, is the generally accepted method in the forensics literature for solving complex DNA interpretation problems. There are no other methods known that will give robust and reliable answers that will reproducibly give correct answers and withstand scientific and judicial scrutiny. An example of one of the many articles in literature is by James Curran from New Zealand. His article, A Markov Chain Monte Carlo Method for Resolving Two-Person Mixtures, in Science and Justice 2 years ago, describes the sort of methods that we're all modeling as we build serious systems. And this graph is taken as part of his probability description. He also gives equations. And I'll label for you some of the nodes in this graph, which are quite familiar to you. At the top, we see a node labeled W for the template mixture weight. In the middle, there's a node labeled G for the unknown genotype. And at the bottom, there's a node for the peak data variation. All of these must be solved in order to obtain an accurate and robust, reliable solution. Next slide. In conclusion, TrueAllele implements a rich probability model with a Markov chain Monte Carlo computational solution. This is the standard approach in modern science and statistics. It describes uncertainty using probability, and it makes full use of this new calculus of Bayesian probability models with statistical search. It truly is the new calculus. If you take a look at journals like the Journal of the American Statistical Association, most of the articles just assume this is how you're solving the problem and either do an application or extend the method. In fact, the reason it's so powerful is the original Bayesian methods required the solution of very hard calculus problems in order to compute posterior probabilities, normalizing constants for the denominator of Bayes' theorem, or for extracting the variables of interest in a marginal probability density. By using computing and these methods to do all the hard integration, all the adding up and collecting of results to produce probability distributions just by counting, MCMC methods can solve virtually any problem, and they're particularly well suited to interpreting DNA evidence. Thank you.